All right, so let's go ahead and we'll get started. We're still working on this first project, which is the clustering. Anybody have any questions? How's that going? Anybody have anything obvious they want to ask? Struggling or not struggling? Got a smile?
I'm at a tipping point where I feel like I'm about to get it.
Okay.
Like mentally, like right there. I want to play with it a little bit. I'm
Okay.
really tired.
Okay, so maybe we'll just, so you don't have any specific question, but maybe we'll get you over the time. Okay, well, let me know what I can do to push you over the edge. Okay?
Go to left. Any question?
Yeah. Yes.
About the access equal function you want
Yes.
to make. How exactly do you want us to kind of, I guess, what kind of idea would you have to implement the values that are going into the function?
So it says it's supposed to take an n by 3 array.
Yeah.
So you're going to pass to it all the data. Okay? And then basically what you need to do is out of that data you need to look and see what is the difference between the largest x and the smallest x, and what is the difference between the largest y and the smallest y, and you need to find the largest, which of those dominates. So is the difference between the minimum and the maximum x bigger, or is the minimum between the minimum y and the maximum y bigger? And whichever one is bigger, you need to make a box of that a cube of that size. So this point right in this case, it's the x's that is what it's the x's that dominate. Okay, so this point is going to have the minimum x value, and it's going to have the same y value as its x value, and it's going to start with a 0 z value. Because z, because of the way this data is, z is the smallest one, and we're going to go up from there. So this is the minimum x, that point is the minimum x and the minimum x in the y position, and the z is 0. Then this is the maximum x, well, I guess it's going to be the difference between the max x and the min x. Okay? In Z. So basically you're just finding which is the largest dimension and forcing a cube to that size. And centering that cube on the smaller dimension, which in this case is the y. And the Z goes from 0 up to whatever that largest min to max is. So all you're doing in that function is looking at the data and then plotting 2 points. And I gave you this little trick. You can make the marker be nothing and the line style be nothing, and it'll plot it, but you won't see anything, which is kind of clever. Okay? Does that answer your question?
It does. Thank you.
Okay. Good. Anybody else? Questions? All right. So the thing I want to cover today is this principal component analysis, which is I've sort of co-opted it for a purpose here, and it's not its typical use. There's a couple different uses. The most common thing for principal component analysis is to take data and to reduce the number of dimensions of the data. Okay, so it's kind of like data compression in a way, that you're going to throw away some information, but you're going to throw away the information that's not very useful. Okay? Now, in this case, what we're trying to use principal component analysis is for sort of a side effect of it. Because when you're trying to throw away some of the information, you want to throw away the least useful information. So what principal component analysis does is it basically finds what are the directions in your data that have the most variation. And that's kind of what we're after. So for example, with all these red dots for this bus, we're trying to find what is the direction where there's the most variation in the data. And that happens to be in this long direction here. That's where the data varies the most. And we're going to use that to help us know what is the direction of the most variation that'll sort of give us an idea in which direction is that bus pointing. That's kind of what we're using it for. Okay? Now, in D2L, I put a link that is a really good link. It's an interactive website here for how to explain sort of what goes on with principal component analysis. Now, like I said, the main purpose of principal component analysis is to take data and reduce it down into smaller dimensions. So here's some data that is two-dimensional data. And what's nice about this is you can sort of move the points around. This is really kind of neat. Okay, so there's 5 points in here. You can move them around. They have x, y positions. They have a dimensionality of 2. There's 2 directions, x and y. Okay, and then down here it sort of gives you what is the projection in x. You know, sort of if you project these down to the x-axis, these are the 5 points. And if you project across to the y-axis, these are the points. Okay? And so what principal component analysis does is it finds in which direction is there the most of the variation, and that's the red direction. And you can see as I move this, it sort of changes where that direction is slightly. You know, and if I change it here, you can see the most now the variation is horizontal. That's the direction of the most variation. And so I can sort of move these things around, and we can see where these axes change. And then when you once you figure out what the direction of the most variation is, then you can take your data and you can transform it into another space. And basically what it does is it makes the x-axis in the transformed space be the direction of the most variation. And the y direction is perpendicular to the direction of the most variation. So essentially what it does, it basically just rotates. It takes this data and it rotates it so that the x direction is the direction of the most variation. Okay? So consider, for example, you're trying to classify, that these 3 are in a class and these 2 points are in a class. Okay? And if you transform that into the other space, okay, you can see that the x direction, that's the red direction, the 3 points are clustered together here and the 2 points are clustered together here, and the y direction doesn't really tell you very much about whether they're in which class they're in. If I look this way across the data, if I look in that direction, this point basically, these 2 points have basically the same y value. So the y is not very useful for discriminating between these 2 points. The x is useful. So I actually could throw away the green direction. I could take this 2-dimensional data and look at it as a 1-dimensional problem. And I could still tell the difference between those 2 classes. So if I reduce the dimensionality, that makes the problem much simpler. But yet I still have most of the variation in the data. I don't need that this second, if I transform it, I don't need both dimensions anymore to tell the difference between those classes. And that's what PCA is mostly used for, is to take a high dimensional data set and reduce it down to a smaller dimension data set by throwing away stuff that is not useful. If I just take the original data set and throw away the 3rd dimension, there's information in that 3rd dimension that I probably want. But if I rotate it in the correct way, then throwing away the last dimension, I'm throwing away the dimension that has the least variation in the data. So you can actually, maybe you have a 10-dimensional space and you transform it into a 3-dimensional space with the 3 directions that have the most variation, then you can visualize it. You can visualize stuff in 3 dimensions. You can't in 10. And you probably can see most all of the variation in the data there. And if you get fancy, you can look at the variances, and it'll tell you how much variance there is in each dimension. You can know whether you're throwing away a lot of information or not. Okay? So that's what it's most useful for. PCA is one of those unsupervised learning techniques that is common, so I sort of threw it in here, not in the way it's supposed to be. It's generally used, but in a different way. Okay? So again, if we go back to here, we're using it only on the data for the bus. So I take all of the red dots, which direction has the most variation, and that's going to be this direction right here, and that's going to be the direction that a bounding box will be a pretty good fit for. Okay. Now you'll notice that these bounding boxes won't be perfect, because you can see, like in this car especially, there's a whole bunch on this side, but on the back side of the car where the LiDAR couldn't see, there's not points there. And if I was to rotate this thing around to look straight down on top of it, you'd see that the bounding box isn't pointed exactly in the direction of the car, but at least it's a good start. Okay? Now, also on D2L, I uploaded a file here that is example PCA. Okay? So I've gone ahead and I've imported from scikit-learn the decomposition module for which PCA is part of. Imported NumPy and Matplotlib. Okay? So I'm going to create, let me go ahead and run this. And I created some data just like we did before. Okay, and here's the data. It comes from a normal distribution with a variance in one direction that's bigger than the other. Okay, so I've got 50 data points in this Gaussian that's an elliptical Gaussian instead of a circular one. Okay, and so then I'm going to define an object of the PCA class. It comes from decomp.pca, and I'm going to tell it I want two components. Okay, so the original data was 2 dimensions. I'm going to have 2 dimensions in the result. So I'm actually not going to get rid of any of the dimensions here. I'm going to keep them both, okay, and I'm just going to basically rotate this data to be in the direction of the most variation. Okay? All right, so then I'm going to fit. Okay, and this is just like you use with a k-means. You do your object dot fit, and you pass the data to it to fit. So that's what's nice about scikit-learn is that it uses the same member functions in a lot of these different classes. So I'm passing it the data, and again, the data is every row is a single data point, and each column is a feature. In this case, there's 2 features. It's x and its y position. Okay, then I'm going to transform the data. So PCA.transform. I'm going to pass in the data and I'm going to transform it. That's going to rotate it so the x direction is the direction of most variation. Okay? Then I'm going to reconstruct it by doing an inverse transform on the transformed data. That'll get me back to where I started. Okay? So I plot figure 1 is the original data. Okay? Figure 2 is when I rotate it to get it in the direction of most variation. Okay? Now the true data, the most variation is exactly vertical, but I've only sampled 40 points, so the direction of most variation is actually a little bit angled to the right of the vertical because of these 50 data points. And you can see that's this direction right in here is the direction of most variation. Okay? And then, of course, when I do the inverse transform, I get it back to here where it's just the original data is back again. Okay? Now, let me do something where I go back here and I'm going to change the number of components to be 1. So what it's going to do is it's going to do the transform, find the direction of most variation, and then it's going to throw away one of the dimensions. Okay? And I think when I run this, I'm probably going to get an error. Yes. Okay? And you can see the transformed stuff only has 1 feature. Okay? And so I can't ask for the column number 1, the second column. That doesn't exist. Okay? So what I'm going to do here, I'll put a comment on this for right now. Okay? And instead, I'm going to say numpy zeros like. So, like trans. And what the numpy zeros, that's just like MATLAB zeros, and you can tell it how large of a matrix you want to have and filled with zeros. Okay? But the zeros like, if you pass to it a NumPy array, it'll create an array with the same size as the one you pass to it. So that's kind of nice. Otherwise, I'd have to extract out what is the shape, the 0th shape of it. What's the first shape of it? I can just pass it the array, and it'll infer from it how many rows and columns it has. So that's kind of convenient. Now I think this will run. Yes. So here's the original data. here is the transformed data, and here's the non-transformed. Now let me run it one more time, get different data, because I want to make a point here. Didn't get what I wanted yet. There we go. Okay, that's good enough. Okay, here's the original data. Here's the transformed data, where it's only one dimension. So basically it looked along this line, and here, that point is this point. And this point here is this point. And then there's 3 points here clustered pretty close together. And then there's all these things clustered close together. Then down at the bottom there's 1 and 2 that are pretty well separated, and then these guys are all big in a clump. Okay, so this is a one-dimensional transform. I've thrown away information, but I know where the point is along this direction. Okay, now what's interesting is when you do the inverse transform, you've actually lost information. You've lost information because you've gotten rid of one of the dimensions. You don't know how far away from, in the perpendicular direction, we don't know how far away each point is. So when I transform back, it knows what direction is the direction of most variation, but it doesn't know how far to put them off to the sides of it. So it transforms them back to the original space as best it can with only the one dimension of information. Okay, so it takes this and it rotates it back into its original space, but it can't push them off of that direction because it lost that second dimension. Okay, so that's just to show, and I don't know, he sent me an email or called me and said he was having trouble getting the inverse transform to work. He was still only ending up at one dimension, and I'm guessing this is what he did, is that he reduced it down to one dimension and then went back and he still only had one dimension, essentially. Okay, now let me go ahead and put it back the way it was. Okay. All right, so let's I should have rotated this data, but anyway, okay. So let's pretend that this data here, well, you know what? Let me do it on here. This might be easier to say. So let's say that these are the points for your car. Those are the points that are in your cluster. And you're trying to find the bounding box. Okay? So if you take this data and you transform it over to here, we know that this is the direction of the most variation. Okay? So if you draw a rectangle, if you were to draw a rectangle around this, it would be like this, right? That would be your rectangle if you drew a rectangle around that. Okay? When the car's actually pointing in this direction. Okay? But if you transform to here and draw a rectangle around this, then the rectangle is actually pointing in the direction of the most variation where the car is pointing. Okay? So what you can do is you transform it to here, and then you can draw your bounding box. Here's going to be one point because it's at the minimum x and the minimum y. Here's a point in your bounding box, minimum x, maximum y. Here's a point on your bounding box, maximum x, maximum y. Here's a point on your bounding box, maximum x, minimum y. Then you take those 4 points and you inverse transform them back to here. Then you'll get the points here, 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 and here. Okay? So that's my idea for how to get the bounding box with PCA. So you need to use transform and inverse transform. Okay? All right. And you got the code for that. Here's the code. It does the transform, does the inverse transform. You just, instead of data here, you're going to have one of the data from one of your clusters that you've identified. Okay? And then once you have it in the transformed state, you need to look, where's the max x, where's the max y, where's the min x, where's the min y, and put the 4 corners. And that's going to be your bounding box. And then those 4 corners is what you transform back. And remember, data is in rows. Each sample is in a row. Each column is a feature. So you're going to have 4 points for your bounding box. There's going to be 4 rows for each of your 4 points, and each is going to have the x and the y in its transformed state. And then when you do the inverse transform, you will still have a 4 by 2 array, but the values in the columns are going to be the inverse transformed x and y back in the original space. Okay? All right. We've got some more time today, and if we don't have any specific questions, let me see what the syllabus. When's the project due? We still got a couple times to work in class here, right? We got. All right, good. So we still got we got still a week and a half, basically. Well, it's due. Yeah, a week and a half until it's due. Okay. So what I'm going to do for the rest of the class today is to introduce some stuff with linear algebra that can show us a little bit more about how this rotation stuff works. It's not actually necessary. When I first wrote the code, I did the inverse transform sort of manually. I was a dumbass and didn't realize there was the inverse transform method there, which is really handy. So I sort of did that myself. And I'll show you sort of how we can do some rotations and stuff. And it's going to be useful because we're going to do linear algebra matrix stuff later on. And we're going to do rotations later on as well. So this is going to be help cement us what's going on now and help us in the future. And we got some time, I think. So I'm going to go ahead and pull it in now. Because I was going to cover some matrix stuff a little bit farther down here. But it gives us a little less time. So I think it's better for us to go ahead and cover it now. All right, so how many of you have not done linear algebra yet? That have not done linear algebra, okay? So this is going to be introduction for you guys. The rest of you guys is going to be a little bit of a review, okay? So linear algebra, basically you're taking matrices and you're doing arithmetic operations on matrices. Okay, and matrix multiplication is one of the most common. Now a matrix is going to be represented by how many rows it has and how many columns it has. Okay? Oh, I hate this. I don't have the screen doesn't show me the same thing. Anyway, all right, so if this is our first matrix, it has n rows and m columns. And this is what's a little confusing is that times symbol, usually we use that to represent how many rows versus columns. That's not multiplication. Okay? I've put the parentheses around here to indicate multiplication. So this is a matrix with n rows and m columns. And if I'm going to multiply it by another matrix, I can't just multiply it by any old matrix. Okay? I have to multiply it by a matrix that has the same number of rows as the number of columns in the first matrix. Okay? Now the number of columns in the second matrix can be different, but these inner dimensions, so-called inner dimensions, must match. Okay? And what'll happen is basically because these guys match, they end up going away. I end up losing that, and I end up with a result that has n rows and p columns. And that's what, if you remember from MATLAB, if you ever try to do multiplication in MATLAB and it says inner dimensions don't agree, okay? Probably you forgot to put a dot next to the times because you were really meaning element-wise multiplication rather than matrix multiplication. But if you were doing matrix multiplication, that would be, hey, this is an error. The m and the m don't match, okay? So here's a real simple example. Okay, this is a 3 by 3 matrix times a 3 by 3 matrix. Now, both of them have the same number of rows and same number of columns. These are what we call square matrices because they have the same number of rows and columns. And this is easy. 3 by 3 times 3 by 3 is for sure going to work out because all the dimensions are the same. But basically, this inner 3 and 3 is what goes away, and I get 3 here and 3 there. Okay, so here's an example. Okay, I've got this matrix here. Where'd my cursor go? This is really annoying. Oh, I'm on the other. Oh, it's because my desktop is. I don't know. Anyway, all right. So here is one matrix 3 by 3, here's another matrix 3 by 3, and this is the result of doing matrix multiplication. And if you haven't taken linear algebra, you have no idea where all of those numbers came from. Okay? You might be thinking element-wise multiplication is 1 by 9 gives 9. 2 by 8 gives 16. No, that's not matrix multiplication. That's element-wise multiplication. And recall, in a NumPy array, if you do multiplication, it is element-wise multiplication, not matrix multiplication. Okay? Which is the opposite of MATLAB. Okay? So if in NumPy you want to do matrix multiplication on arrays, you have to use the dot command. So I've created A, I've created B, I printed A, printed B, and then I printed the result of dotting A and B, which is a little confusing because normally we think of dot as the dot product, which is a special case of matrix multiplication. But for whatever reason, NumPy uses the dot product and matrix multiplication in the same function, which is a little weird, but just takes some getting used to. And here you can see we got the same result as what I wrote up there. I'll get to it again in a minute, how we got that result. Okay, so let's do a different case. This is where the inner dimensions do agree, okay, but it's different from the number of rows and columns. So 3 by 1 times 1 by 3, I end up with a 3 by 3 matrix. Okay? And so if I have this as my 3 by 1 matrix, this as my 1 by 3 matrix, well, this is the result I get. Basically, I copy this into every row. And again, I was a dumbass and didn't realize in MATLAB that there was the mesh grid. And I thought I was so cool because I used matrix multiplication to create my mesh grids. Like, I'm so fancy and like, well, dumbass, just use mesh grid, you know. So I did eventually learn that, and it's a whole lot easier because I always have to remember, well, which one goes first? Do I have the ones on the left or the right? But anyway, so that's where the inner dimension disappears. Okay? Here's the special case I was talking about. If I have a 1 by something times that something by 1, the inner dimensions go away and I'm left with a 1 by 1 matrix, which really is just a scalar. Okay? And so here's one guy and here's another guy. Now, what's really nice, there's something I need to explain over here. No. Yeah, okay. Okay, what's nice in NumPy is that because this is a dot product, you don't actually have to get the dimensions correct. Because technically when you do NumPy array, this is a one-dimensional vector. It's not an array, it's not a matrix. And this is a one-dimensional vector. So I sometimes think when I write that it's a 1 by 3 matrix. A 1 by 3 two-dimensional array because I'm thinking MATLAB. But in NumPy, this is actually one dimension. It doesn't have a number of rows. It only has a number of columns. And if you look at it, if you look what the shape of that is, it ends up being 3 comma, parenthesis 3 comma parenthesis. It's a tuple with one thing in it. Okay? So here it takes a one-dimensional vector dotted with a one-dimensional vector. Normally you would have to make sure one is a row vector and one is a column vector, but NumPy doesn't care about that. And you can see it gives the value of 10. And that is 1 times 3 plus 2 plus 2 times 2 plus 3 times 1. 3 plus 3 plus 4 is 10. Okay? Now, along those lines, I had to do something a little special over here. If I had just said A equals NumPy array 1, 2, 3, and I said B is equal to NumPy array 1, 1, 1, it wouldn't have worked because it would have done a dot product of those two vectors. It would not have done the matrix multiplication of a 3 by 1 and a 1 by 4. So that's what I did here. By forcing it, I created it as ones and forced it to have 3 rows and 1 column. So this is actually a two-dimensional NumPy array, which is different from this thing. This thing here does not have the same shape as that guy. One is a one-dimensional NumPy array, another is a two-dimensional NumPy array with a single row. Okay, so this is a single column. This is a column vector, this is a row vector, and then kind of annoyingly, after I created its size, I had to go in there and change each of the values of b. Okay, by saying the 0th row, 0th column, 0th row, first column, 0th row, second column. Okay, so if you want to do matrix multiplication with NumPy arrays, you have to force it to turn it into a 2D array. And this is a case where using a NumPy matrix instead of a NumPy array is useful, because a NumPy matrix always is 2 dimensions, and when a NumPy matrix, when you do the multiplication symbol, it does matrix multiplication. Okay? Now, when I first started working with NumPy, I said, well, screw the arrays. I'm used to doing MATLAB where everything's a matrix, and I can make everything a matrix. Okay? But then I found out that it's actually more painful when I'm dealing with single rows or single columns with a matrix than it is to deal with them in an array. So I sort of went back and said, okay, I'm going to remember that multiplication with an array is element-wise and the dot product is the multiplication one. So I personally found it more convenient to work with NumPy arrays instead of NumPy matrices, but you could do either one. So I work pretty much exclusively in NumPy arrays, but there's really no reason why you couldn't do the matrices. Okay. So that thing's called the dot product, sometimes called the inner product, because it's that inner 3x3 that all gets the multiplication stuff. It's also called the scalar product because it results in a scalar instead of a matrix. Okay. All right. So what are the details of the matrix multiplication? Okay, so you can write it in words and say that the value of the ith row and jth element in the new matrix is the dot product of the ith row in the first matrix and the jth column in the second matrix. So you can write it in words, and it's really confusing and it makes no sense, but it's actually completely mathematically correct to say that, but it's really hard to understand what that means. So let's go to the example that I had before, and essentially in order to get this number here, this is row 1, column 1 in the final matrix, right? So I need to create that using row 1 in the first matrix and column 1 in the second matrix. And I take the dot product of those two, that row and column. And that's going to take the 1 times the 9 plus the 2 times the 6 plus the 3 times the 3. And that's where the 30 comes from. Okay? Then, this number here is in the second row, first column of the final matrix. So I need to use, it's the second row, first column. So I need to use the second row of the first matrix, the first column of the second matrix. Dot product them. 4 times 9, 5 times 6, 6 times 3. Turns out that gives me 84. This thing here, that is in the third row, first column of the final matrix. So I use the third row of the first matrix, first column of the second matrix. 7 times 9, 8 times 6, 9 times 3 gives 138, if you care to work out the arithmetic. Okay? Then this guy here, that is in the first row, second column of the final matrix. So I use the first row and the second column of the second matrix. Okay? 1 times 8, 2 times 5, 3 times 2. The 69, second row, second column. Okay? Second row, second column. That guy, third row, second column. This guy is first row, third column. This guy is second row, third column, third row, third column. So basically I'm taking the rows in the first matrix and the columns in the second matrix and doing all the combinations of the dot products between them and placing those 9 combinations of dot products in this new matrix. Okay? Now, you can ask yourself, what moron came up with this, and why is this even there? Right? I mean, somebody decided to do this for the first time. Okay? And it's not because, the math gods spoke and this is what matrix multiplication is. Okay? Nobody knew that. Okay? But what we found is that if you define matrix multiplication in this way, you can do an amazing amount of really, really useful things. It's shocking the amount of useful things you can do if you figure this out. Okay? So, math isn't that's not like that's the way it has to be. This is truth. It's not truth. Math is not truth. There's probably going to be mathematicians going to argue against me. I guess I come from it from a engineering perspective, but basically this is just a tool that we figured out how to do useful things with. That when we were cavemen, we saw lightning strike a tree and a branch fall off. Like, what's that branch over there? Oh, bang! It hit me on the head, man. That's not very nice. But if I pick that up, I can whack a mammoth with it, and maybe I can kill it. It's not truth that this tree is a weapon. It's just I've figured out over time that it's useful for me to do something that I want to do. Okay? That's the same thing here. That all this math stuff, it just happens to be useful for us to solve things and fix things in our world that we want to fix. Before we figured that out about the stick, we could only eat nuts and berries. Now we got mammoth meat. That's awesome. Okay? We can do all sorts of great things with these matrices. Okay? So, here I do matrix multiplication manually in Python. Okay? Where I define my A and my B. Okay? And then I predefine the size of C. I make it empty. That means it has no assigned values, but the same size as A. Ooh, that was dangerous. This code is not general. I need to change that, okay? At least the for loops are general, but that C is not general. I need to make that empty where it has the same number of rows as A and the same number of columns as B. I got lucky because A and B both have the same number of rows and columns. So I got lucky there. That's not general code. I need to change that to be empty shape A.shape 0, comma B.shape 1. That's what that should have been.
So what are the shapes? Because I was looking at the Python primer and I couldn't figure out.
Okay, so shape is a data member of the class. Okay? So here, look at this. So here, look here. When I do B.shape, you notice there's no parentheses here, right? So that's not a function call. Okay? Do you remember when we did 2610 and we did C++ classes, and you could have a data member or you could have a member function, and the data member stored information and the function was something you could call? Okay? The NumPy array has member functions where you call things, you have parentheses, and you pass input arguments. It also has data members. Okay? So this array not only has the values that are in the array position stored in it, but it also has a data member that says what the size of it is. So shape is a data member, in this case, that has two elements. The 0th element is the number of rows that A has, and the first element is the number of columns that B has. So B.shape bracket, that bracket is an indexing tool. So I'm indexing, give me the first index value stored in, it happens to be a tuple, in the tuple of shape. Okay, so it's a data member. So if that's a little weird, you need to go back to when we created classes in 2610 and think about data members versus member functions. Okay? And if you're still worried about that, come to my office hours and we'll get you straight. Okay? So, for now you can just memorize. If I have a NumPy array and I do period shape, that will return a tuple with the number of rows, columns, and depth, or whatever dimensions it is. If I do the numpy array dot shape bracket 0, that gives me the number of rows. Bracket 1 gives me the number of columns. Okay? All right. And so I've got a for loop, loops through each of these. It pulls out, it does the dot product between the row of A, the colf column of B, and puts that in the row column position of C, and you can see I get the same thing. Okay? Now, there's this thing called the identity matrix. And it has zero, it's a square matrix, it must be square, it must have the same number of rows and columns, it has ones along the diagonal and zeros everywhere else. Okay? And they call it the identity matrix because if you take any matrix A and multiply any matrix A by the identity matrix, okay, again they've got to be square, okay, it'll give me that A back. It's the identity. In normal arithmetic, the identity is 1. So if I take anything and multiply it by 1, I get that anything back. So in matrix multiplication, the identity is the identity matrix. So if I take a matrix, multiply it by the identity matrix, I get that original matrix back again. Okay? So for example, that multiplication gives me the same thing back again. Okay? That, and this is kind of cool. Let's do the manual thing. To get this guy here, I have to do dot product that with that. Now you'll notice there's only 1 1 and the rest are zeros. So that basically plucks out the 1. Only the 1 goes. The 2 and the 3 get zeroed out. Okay? Then when I multiply these guys, the 4 stays and the 5 and the 6 get zeroed out. There I multiply that, the 7 stays, the 8 and the 9 get zeroed out. Okay? Then, when I go to the second column, here now the 1 and the 3 get zeroed out, the 2 stays, the 5 stays, the 8 stays. Okay, then I go to the third one, I'm dot producting 1 times 0, that's 0, 2 times 0, that's 0, 3 times 1, that's 3. Add them together, I get 3. The 3 stays, the 6 stays, the 9 stays. It's kind of interesting. Okay? Now it doesn't matter, I can pre-multiply by the identity matrix or post-multiply by the identity matrix. I still get the identity. And that's one problem that we need to be careful of with matrix multiplication is it is not associative. A times B is not B times A. And the most obvious reason why that is because inner dimensions need to match. Okay? So we need to be a little bit careful of that. So here's some code for doing the identity matrix. There's a command called I, spelled E-Y-E. Okay? That's the same in MATLAB as it is in Python. And you need to tell it how many rows you want, how many columns you want, and then you dot product A and I, you get A back. You dot product I and A, you get A back. Okay? Then we have a matrix inverse. Okay? So, this is, if I have a matrix, what do I need to multiply that matrix by to get the identity matrix? Okay? And so we notate the inverse of a matrix by putting a -1 raised to the -1 power. Okay? It's not really raised to the -1 power, it's the inverse. Okay? So be careful, it's a little weird with that notation. It's not 1 over A. That's not the same thing as an inverse. Okay? And so we can get the inverse in NumPy. You do numpy.linalg, linear algebra, dot inverse. You pass to it the matrix you want the inverse of. And there are only inverses of square matrices, by the way. You can't get an inverse of something that's not square. Okay? And this will return, here will return the inverse of A. And then if I matrix multiply with dot, A times the inverse of A, I should get the identity matrix. Okay? First I printed A, there's A. Then I printed the dot product of A times its inverse, and here you can see I got the identity matrix at least to how the working precision of the computer. There's essentially ones along the diagonal, and there's essentially zeros everywhere else. Okay? All right. So this is all like theory and stuff, and like, the math god said it must be so. Okay, how can you use this to do things? Okay, and one of the examples, and I have a little bit of time left here, 5 more minutes, okay, is with a rotation matrix. Okay, so if I have data points, x and y points, and x and y points, and I want to rotate that information somehow. Okay, I can rotate that with a matrix. I mean, I could just do a bunch of trigonometry to figure that out. And basically, what's boiled in here is if you work out the trigonometry, this is what you're going to get. Okay? So if you work out the trigonometry, it's going to end up being the same calculations. It's just compacted into a matrix form, and it makes it more convenient to program rather than writing a bunch of lines to do the trig. Okay? So you can see, you can imagine if you had an x thing here and a y thing here. If you had x and y and you multiply that, x times cosine theta, y times sine theta, you're starting to see how this might turn into a rotation. Okay? So you have to trust me on the trigonometry, but you can go and derive that this is true. Okay? So this is a little modified from the way you normally see a matrix rotation, because the data in our case, we have n data points and 2 columns. And usually you're doing this with 2 rows and multiple columns, oftentimes. Okay? So if you have a bunch of data points that you want to rotate, where you have lots of things in every row, and you have 2 columns, x and y points, okay? If I multiply that by this 2 by 2 rotation matrix, you can see the inner dimensions match, and I'm going to be left with an n by 2 thing in the end, where this is the stuff that's going to be rotated. And if I do this, my B information is going to be the A rotated clockwise by theta. Okay? So the A is the original space, the B is the transformed space with the rotation in there. Okay? Then, if I want to go back the other way, if I want to do the inverse transform, I can apply this stuff that we already saw here, these linear algebra rules that we've talked about, where I'm going to take both sides of the equation and multiply by the inverse of R, whatever that happens to be. Okay? R times R inverse, that's the identity matrix. A times the identity matrix is just A. Okay? So that means if I take B and multiply by the inverse of R, I'll get A back. So I can do the inverse transform by taking the B, multiplying by the inverse of R, and I'll get my original data back. So I can do this same transform, untransform that I was able to do in the PCA stuff. Okay? So here's an application of why we wanted to mess with all these matrices and the rows and the columns and the inverse stuff and the identity stuff, because it's useful for us here. We just have to do a matrix multiplication, it transforms me. I have to do another matrix multiplication using the inverse, and it untransforms me, which is kind of neat. All right, so I don't have a lot of time, but so useful. Okay, in here, basically what I've done is I've accessed the data members of my PCA that are called components underscore, and they give me the vector x in x and y. So here's my data, figure 1. Okay, the vector in the x direction is not very strong. The vector in the y direction is very strong, because most of the stuff is in this direction. Okay, so the y component's very strong, the x component is not very strong because there's not much variation in that direction. Okay, and so I've taken those two components, I do an inverse tangent on them to get the angle from that vector, and that's the angle that I want to rotate. Here's the rotation vector using that angle. Here's the inverse of the rotation vector that I'll need later. I'm going to dot product my data times the rotation. That will give me the rotated points. Okay, I plot them, and then I take my rotated points, do a matrix multiplication by the inverse, and it will undo the rotation, bring me back to my original data. And if you look at all the data here, you can see it basically does the same thing as what the PCA transform and untransform do. And class is over, but you can mess around with that and look a little bit at it. But basically, figure 1 was the original data. Figure 3 was doing the PCA transform and untransform. This is doing it manually, transforming and untransforming. Here's PCA's transform. Here's my transform manually, or one of them, it's the other way. This is the PCA transform. This is my transform manually. You can see the only difference is the direction that it rotated. The PCA rotated it counterclockwise. Mine rotated it clockwise. Okay? So here I've shown you once you get PCA, and PCA gives you the components, that you can do the transform and untransform manually if you wanted to. But obviously it's easier just to use the transform and inverse transform in the PCA. Don't be a dumbass and look and read the documentation so you don't have to do all that extra work to do the inverse transform. Okay? So, linear algebra, matrix stuff is really useful. I look back on my time, I didn't have a very strong linear algebra course. There's so much linear algebra stuff I wish I understood better because it's so useful in machine learning and computer vision. So if you haven't taken linear algebra, you now have extra motivation when you do have that class to pay more attention. All right, thank you guys. Next time we'll just come prepared with your question, be working on your code, and we'll just sit down and work on stuff, and I'll do whatever we need to help you guys get set.